Good morning, students. So finally here we are, Chapter 7, Atomic and Nuclear Physics. So I would like to start discussing this topic with you, showing you a picture of a very famous power plants they used to exist. This is Chernobyl, a place where, well, it's one of the most well-known nuclear accidents in history, greater than the Fukushima power plant. It's the largest problem that we've ever had in recorded history regarding nuclear materials, right? So radioactive particles. And basically in this chapter we're going to discuss many things, many concepts, and understand a bit more of what's happening underlying on those with those particles, and then we'll understand what happened here and how can we harness the power from the atom. So just for a minute, let's assume the planetary model of the atom. So we have the nucleus, which is just like the sun in our system, and we have the electrons orbiting in shells around it, in orbits around it, if you want to call it like that. Now, there will be some force of attraction, right? Since this is negative and this is positive, right? The electron is negative, and then in the nuclei you're going to have protons which are positive. So there will be some electromagnetic force here, and they want to get close to each other. So let's say that you want to take this electron away, and you want to take this electron so far away that you would not feel anymore the pull of this nuclei. And how much energy, how much work would you have to put to get this particle away from this between quotes gravitational pull? It's not gravity, it's electromagnetic. So but it's just like the planetary model, right? So if I was bringing this so far away towards infinity, how much energy would I have to put? How much work would I have to do? So to answer this question, we have to discuss what are the energy levels. So we have found out, even though this model, the planetary model, is not exactly what's happening, there are loads of weaknesses which we're not going to go into detail in this course. However, it's okay for some applications. It's okay to assume this. But now, what are the energy levels? Well, basically, electrons, they're not going to be anywhere around the nuclei. There will be certain orbits, and well, assume that those are actually well drawn, right? So basically, electrons, they are stuck to the orbits. If you give them energy, they will give or take away energy. They will move between those orbits, either inwards or outwards. So you can think of this as a planet, for example, and things orbiting it, like satellites, the space station. If the space station loses energy, wouldn't it fall towards the planet? It would. So when your electron loses energy, it goes into a place which is closer to the nuclei. When it gains energy, then it goes away from the nuclei. It has more energy, so it may spin faster. And if you remember your gravitational laws, your circular motion laws, the faster you're spinning, the further away you might get from your pull. So let's take the atom of hydrogen, since it's very simple. So I've put here two different ways to express the energy levels for hydrogen. So what does that mean? Well, the energy level 1, 2, 3, 4, the lower numbers are the closer, the ones which are closer to the nuclei. So the first energy level would be this one, the second energy level would be the one coming after, and so forth. So for me to take one electron from this layer, right, from this orbit, away from my atom, I would have to put this much energy. If if it was in the second orbit, I would have to put this much energy, and so forth. And you can see exactly the same numbers here. The units, they make much more sense to be calculated in electron volts instead of joules. And usually, for example, a very common thing they ask you is, how much energy do I have to give to this um, electron for it to go from the ground state to the first excited state? And then you just work out the difference. How much energy would you have to give? Well, it's this much less this. So it would be about 10.2, right? 10 point something around that. And that's quite simple, right? So we have to put energy into our so we put some energy, we do work, and the electron will go towards an outer orbit. Now there's also another interesting thing that happens. It just happens that sometimes electrons, they will go towards a less energetic state. So here they're losing energy. So when they lose energy, they will release a photon. And we can see that. That's visible to us. That's something that we can, if you remember, right, when you have chemical reactions, you will be able to see something, smell something. You can appreciate that with your, you can appreciate that with your senses. So we can see light. That's why, for example, cesium, the radioactive isotope of cesium, glows. So, for instance, cesium 137 is a radioactive isotope. So isotope means same number of protons. And protons are actually what define an element in the periodic table. So in nature, for example, hydrogen, we not only have hydrogen, which we know with one proton, right? However, we may have hydrogens with more neutrons. So that's an isotope. We have the same number of protons but different number of mass. Anyway, so cesium, one of its isotopes is radioactive, which is this 137, and it glows. It glows in the dark. It looks like this picture here, blue, faint blue. So there was a case many years ago in Brazil in the late 80s where some people, they found out in a dumpster some cesium 137, which was some leftover from some imaging equipment, some medical equipment, and they found it. They took it home. Some kids ate it, and many people died. People got on the bus with that, and it was a huge problem. It was a huge issue. So this was like the container where it was found, and this is the hand of one of the people who got in contact with it. It got much worse than this, but I'm not going to show you. You can do some research if you want. Cesium 137, but it's quite gross, and yeah, it's shocking. So it is dangerous, but it's dangerous if we don't know what we're doing. Because most of those radioactive particles, they happen in nature, naturally. We just have some ratio of what's radioactive and what's not radioactive so it doesn't damage us. So basically we enrich our substances, so we raise the percentages of what's radioactive. So let's say, for example, because there is some ratio, common ratio of isotopes in nature. For example, carbon dating uses the ratio of isotopes of carbon, comparing different isotopes of carbon to find out the date of something, because it changes with time. When we die, well, when we're alive, we have a certain ratio of the different kinds of carbon atoms that we have, the different isotopes of carbon. After we're dead, some of those decay. So some of those, they will become different isotopes, and by comparing that ratio, that's how we measure the age of things using carbon dating, because we know about how long would it take for half of that substance. So we know the half-life basically, which is a concept that we're going to cover in the future, but we know how long it takes for that substance to decay, for that substance to change, for that substance to become an isotope of itself, a more stable isotope. What happens here is that cesium 137, and that's just an example. I could get uranium, I could get plutonium. There are loads of different elements that I could use as an example here. Cesium is just one of them. So what happens that cesium 137, it's unstable. So it wants to get to a more stable condition. So it wants to become an isotope which is more stable. So it's releasing particles all the time. And those particles, they are what damage us. And not only that, when the electrons, when they move from one layer to another one, they are going to release light. That's why cesium glows in the dark. Now, observing this phenomena, scientists have analyzed and measured that actually, well, when we get this atom from a more excited state into a less excited state, so I'm getting this electron to go to an inner layer, some energy is going to be shut off, and this energy that we call photon, that's light, that's visible light, it's also measured in what we call, quanta. Now, quanta, they're actually finite values. So basically they are packets of energy. They are the smallest packets of energy that we can have. You cannot have half a quanta. One quanta is the smallest unit of energy that we have ever found in nature. So how can we calculate the energy of a wave, of one of those? Because photon is a wave, right? It's a wave which is emitted, and that wave might have different frequencies. So if you want to calculate the frequency, and there is a relation between the energy of this photon and it, or a wave, and its energy and its frequency, sorry. So E equals FH, or HF. Now H is a constant, that's Planck's constant, which is about 6.63 times 10 to the negative 34 joules second. So that's Planck's constant. And F is the frequency in hertz of your wave. And energy here, since this is in joules, this is in seconds, energy here would be in joules. You might have Planck's constant in electron volt something, right? So you might have some measurement of energy which is more appropriate, just like we had before when we had our energy levels. Now you can also combine this equation with the wave equation, C equals lambda F. And since this is light, we know that this speed is 3 times 10 to the power of 8 meters per second. But now there's a point here. This is a two-way lane. So not only if an electron goes into a less excited state, it releases some photon, but also if there is a photon hitting our atom here. So if one of our electrons absorbs the energy from that wave, it will move to an outer layer, a more energetic layer. So it will absorb the energy of that photon, and it will then move to an outwards layer. If you give enough energy, what would happen? Well, you would ionize your atom. So you would basically strip it of its electrons. So, if I showed you this table again, I asked you, okay, how much energy do you have to give for the hydrogen atom, for an electron to go from energy level 1 to 2? So you work out this difference, right? So how much would this difference be? So the change in energy is negative 3.39 minus minus 10.19 electron volts. Now if we convert this to joules, right, so we basically multiply by how many joules would 1 electron volt be. So it's 1.6 times 10 to the negative 19 joules per electron volt. So then we can cross out the units and we're going to have our result in joules. So if we work those numbers out, we would get 1.2 times 10 to the power negative 7 meters. So this is, if we put in a more meaningful way, it's 120 nanometers. Oh, sorry, I messed it up. Sorry, nothing to. So if we need 1.6 times 10 to the negative 18, we can use the formulas that I showed you before. So E equals lambda, sorry, HF. H here is the Planck's constant, and C equals lambda F. This is the wavelength, this is the frequency. Since we want to find out the wavelength, right, we can rewrite both in terms of frequency. So frequency is going to be energy over the Planck's constant, but it's also speed of light divided by the wavelength. So if we want to find out the wavelength, we would basically have our energy divided by Planck's constant times the speed of light. So if we put all of those numbers in, so 1.6 times 10 to the power of negative 18 joules over H, which is Planck's constant, that's 6.63 times 10 to the negative 34 joules, so joules, right, joules second, and, oh, this is in fact 1 over lambda. I just flipped, unfortunately, and 3 times 10 to the power of 8 meters per second. So if we work that out, so if we put this in our calculator, I just flipped it wrong here. Now, lambda would be 120 nanometers. That's what I had before, the numbers that I had before. So this is ultraviolet. So this is basically why ultraviolet light is dangerous to us in excess. Because ultraviolet light basically strips us of our electrons. It makes the electrons of our hydrogen molecules go away. It's exactly the frequency that they need. So, very quick example here. We've got here helium. Alright, that's not hydrogen. So this is helium, and it's a an ion of helium, right? So it has been already stripped of one of its electrons. Now, if you remember, helium, right, it would expect to have its proton, two protons, so we would expect it to have two electrons. So if it's +1, it's because it has lost one of its electrons, so it has one electron. So those are the energy levels. So let's skip this first question because it's too easy. Now, B, determine the frequency of the photon emitted by an electron transition from level 4 to level 2. So what you have to remember is whenever you're working with some transition, this works with speed, acceleration as well, it's final minus initial. So final, right, that's your change of energy. Final minus your initial. So our value here will be negative. And what would this mean? What does it mean for this value to be negative? So this means there is a loss in energy. Well, why? Well, because when the electrons they go towards the lower energy level, they're going to release energy, and that's how much energy is going to be released. Now, since the question is asking us for the frequency of the photon, we will still have to work with those numbers, right? So we can use E equals HF. This is our Planck's constant. This is the frequency. So we can rewrite this as frequency will be energy divided by our Planck's constant. And this would be 10.2. Here it doesn't matter if it's positive or negative, because the negative sign means the waves are going out, right? You're releasing energy, you're sending waves outwards. If this was positive, then you would need waves coming in to give energy to the system. So here, if I just put the number, it would either mean the frequency of the wave which is being sent outwards, or the wave which should be incoming for this transition to happen. Okay, so it's 10.2 electron volts, so we would convert this to joules, so we just multiply by 1.6 times 10 to the negative 19 and divide all of this by our Planck's constant, so 6.63 times 10 to the negative 34, and that should be 2.4 times 10 to the power of 15 hertz, right? If you remember your waves chapter correctly, hertz is per second, so that means, well, a few a few trillions, perhaps quadrillions cycles per second. That's quite fast, right? That's a very large frequency. Now, if you take a look at any table for frequencies, you're going to see that this is ultraviolet. This is in the ultraviolet spectrum. So yeah, so ultraviolet, that's letter B. State which region would this emitted particle belong to. Now, letter A, explain why the ground state has a much higher energy level than that of hydrogen. Well, the hydrogen atom has a single proton in the nucleus, but helium, the helium atom has two. So this means that the attractive force between the nucleus and the electron is greater for the helium nucleus. So the helium electron is more tightly bound to the nucleus, and therefore it will require more energy to remove it from infinity. So that's why this value is much larger than what we had when we were discussing hydrogen. Because the more protons you have, the more positive particles you have here in your nucleus, in this case it's 2, the stronger the force to keep the electrons orbiting it. So that's why it has a higher energy level than of hydrogen. And I think that's fairly reasonable for today. Next, we'll go into emission spectra.